Welcome everybody to a lecture today about model regularization. So you have already now heard quite some, you have some amount of machine learning being provided, machine learning techniques. I find it always important to remember the basic principles and the basic building blocks of machine learning. So let me now ask you, what are three main components of machine learning? Do you remember three main components of machine learning that you have come across so far in this course? Please use the chat. Data, yes, data. A model and a loss. What is a model? What do I mean by model? Do I mean Johnny Depp by model, a male model? A model is a set, big set, typically infinite set of different hypothesis maps. What models did you hear about so far? Which type of such predictor maps or hypothesis maps did you hear about? What's the most simple set of hypothesis maps? Linear maps, yes, the linear model. Linear model is the set of all linear maps. Polynomials, so polynomial regression, the model is the set of all polynomial functions with a given degree. Yes, so let's just look at a few examples. It might not be always so obvious that these three components are present in machine learning, but let me share the slides of a previous lecture. Where do we have it? Here. So here was a lecture about classification methods. And yeah, here was a problem. So we see machine learning is often about solving optimization problems, and a large class of such optimization problems belongs to the principle of empirical risk minimization, which I have told you about in the second lecture. So here's an example of empirical risk minimization, which aims at finding a hypothesis with minimum loss. So in this expression, yeah, can you see my slides, by the way?
Yes.
Yes, very good. So which part of this somewhat menacing looking expression, which blocks here correspond to the model or the hypothesis? Which symbols here represent the hypothesis? The weights, yes, there's a parameter vector. So this here, this parameter, these parameters or weights, forget about the superscript at the moment, but these represent the hypothesis. So there seems to be some way that these weights define a hypothesis. I'm not sure. In this case, it might be a linear map, but it doesn't really matter that much. You just have a map that depends on a parameter. Okay, so here's the hypothesis. Where do we see here the loss function? What is the loss function here in this expression? The first sum, yeah, so this is the sum of squared errors. So this here inside the brackets is a prediction error. It's the difference between something that we get out of this. So it seems this here is the hypothesis. This here is the hypothesis map, a linear function that reads in the features of a data point and outputs a prediction. And we compare this prediction to this here might be a true label of a data point. So this here is a prediction error, and we compute the square. So this is the squared loss, and we sum it over all data points in our data set. So this is some average loss, average squared error loss. But there's another term here. And this, you could say, also belongs to the loss function. Remember, the loss function might depend on the data points, so this here, but might also depend on the hypothesis. In its very general form, a loss function might also depend on the hypothesis. For example, might depend on the squared parameters or squared weights of the hypothesis. So this part here is just another component of a loss function. We could define a loss function being the squared error of the squared prediction error plus the norms of the weight squares. We can define such a loss function. And today we will see that there's a general principle for designing such loss or for defining this additional component of a loss function, which is called regularization. So regularization techniques, you can think of them as a specific way to design loss functions. You add regularization terms into loss functions for a certain reason, which we will talk about in a second. Okay, so here, do we have all components? We have data points. Here are the features and the label of a data point. We have a hypothesis map, and we have not only one hypothesis map because we vary. We try out all possible weight vectors. So we try out all possible linear maps. So we search over a model, linear model, a set of linear maps. And we have a loss function, which defines the objective function. And we then want to minimize it. So machine learning is about solving minimization problems, which we call empirical risk minimization problems sometimes. Okay, yeah, in general, again, today we use the following drill. If you want to have a question, if you have a question that you want to have answered immediately, so by some TA or other course stuff in the background, use the Q&A of Zoom. If you want to, if you have a question or a comment that you want to have addressed by me or discussed by me, the lecturer today, please use the chat in Zoom, the Zoom chat. Okay. So yeah, just to show you what you have seen so far is basically combinations of three components: data points, a model. So here the set of all linear maps, could be also the set of all polynomials, or the set of all functions that are represented by an artificial neural network. This is then called the deep learning method. This is the second component, the model, and then we have a loss function. We need some measure that tells us how good is a particular choice for the hypothesis, how good is a particular choice for the parameters here of a linear hypothesis. And once you have these three components, you plug them together in the form of an optimization problem. And then you get a machine learning algorithm by applying an optimization method to this minimization problem. Does anyone of you know optimization algorithms? Does anyone of you know very simple, efficient optimization algorithms? Yeah, Bayesian optimization. Yeah, gradient descent, gradient methods. Gradient methods, they are very powerful, very simple. We do not touch gradient descent into much detail. You have heard about iterative methods for finding the best weights in the lectures by Professor Sick, but I will not go into more detail about gradient methods. There are then optimization courses and advanced machine learning courses which look into more detail of gradient methods, but many, or if not most, practical machine learning methods that you use nowadays in real life, so to say, they are based on applying a gradient descent to an optimization problem that you get from combining data points with a model and the loss function. Okay, so let's now continue to the actual topic of today, which is regularization. So what I want to teach you today, and we will use the first half of the 2 hours today for this regularization. In the second half, we will have the pleasure to hear about machine learning applications at the city of Helsinki. But for this first part, I want to tell you, to give you a quick recap of the workflow in machine learning. So we want to train a model, validate and select between different models. Then I will try to give you an basic intuition about regularization, and in particular, maybe the most important part of this lecture is to show you how techniques for choosing loss function or regularization techniques, which are naturally always defined and explained by specific loss functions. You add this regularization term, you add a squared of weights in the loss function, how this is actually equivalent or a dual view on a data augmentation technique, which might be more natural. Data augmentation, already as it sounds, you augment your data set with more data points, because as you might have recognized, the more training data you have, typically the better the machine learning algorithms will do. And regularization is, in a sense, an implicit way to do data augmentation. Okay, so just to recap what I basically just told about before. In machine learning, we combine three components. We have data points. We know the features of a data point, which is X here, the feature vector X, or in Python, we use numeric arrays, NumPy arrays, to store the features of a data point. And we have labels, the quantities of interest of a data point. So what we want to do in machine learning, we want to find a hypothesis, which is a map that reads in the features of a data point and outputs a prediction of the label. Typically, we do not know the label except for some data points, which we call a labeled data set or a training set. So we can use this training set to try out different hypotheses and measure the quality of their prediction. For example, one way could be to, where do I have it here? One possible loss function is we take the predicted label value for the ith data point, which is the result of applying the hypothesis to the features of the ith data point. And then we look at the difference to the true label value, because we are lucky for the training set, we know the true label values, and compute the squared value of this. This is the squared error loss. But there are also many other loss functions. It's a design choice. The loss function is a design choice. The model, that is the set of hypotheses over which I want to find the best one, is a design choice. And yeah, also which features you use is a design choice. And also the label, by the way, the label, what you consider as a quantity of interest, is a design choice. And you define the machine learning problem in a certain way, in a certain sense, by defining the label. If you define the label, the meaning of a label, you define a machine learning problem. Okay, so, but what is important here, this empirical risk minimization, so this optimization problem that we obtain, which is to find the hypothesis or to learn the hypothesis that has the smallest average loss on the training set, is just an approximation. It's not really what we want to solve ultimately. What we want to have ultimately is to have find the hypothesis which has the smallest risk or expected loss when we average over any possible data point. And this is just an informal goal, because what does it mean, any data point? And one way to define the notion of any data point is by using a probabilistic model or a probability distribution and computing the expectation with respect to this probability distribution. However, we rarely know the probability distribution of the data. We only know a finite set of data points. And one way to solve this challenge is to assume that these data points that we observe, they are IID realizations of the probability distribution that is underlying this expectation. So we can use some basic results of probability theory, which go under the name the law of large numbers, to approximate this expectation with this sum here. So this sum is an approximation of an expectation. And sometimes this approximation is good, and sometimes it's not so good. So typically the optimal hypothesis regarding the training error or the training set is not the same as the optimal hypothesis regarding the risk. And when this difference between the training and the risk is big, then we call this situation overfitting. And in a certain sense, in regularization, what we want to do is we want to find a better approximation of the risk. So we want to find a better loss function or objective function that is based on the training set, because only the training set we know, but is somewhat closer, the minimum of this new objective function is somewhat closer to the minimum of the risk. And one way to change this loss function is by adding this term, these squares of the weights or parameters of a linear function, for example. By adding this term to a given loss function. So the loss function could be here the squared error loss. We use here the squared error loss, and we add a regularization component. We change the loss function, we get a new loss function, and with the hope that the new loss function results in an objective function that whose minimum is closer to the minimum of the risk, because this is what we're really interested. This is our goal. Here's the heart. Okay. But so far, we have already seen a few tricks to solve this problem or to handle this challenge, that the training error has a different minimum, or the minimizer of this training error, which is the learned hypothesis. So this minimizer here is the learned hypothesis. This is the hypothesis, or the parameters of this hypothesis are the one that you get by using the .fit function in Python. When you use the .fit function, for example, for linear regression or for polynomial regression, as you already have done or are currently doing in the coding assignments, the .fit function determines the hypothesis or the parameters of the hypothesis with minimum training error. And this might be not the hypothesis that minimizes the risk, which might be this here. Okay, so one way to first of all detect such a situation is to use validation. So what do? We split the trainings, we split all the data points that we have into two subsets. One subset is called the training set. This is the one that we use to compute the training error. So this is the one that is used to construct this objective function that we want to minimize with the .fit function. Okay. And the second subset is called the validation set. And we try out the trained or learned hypothesis on the validation set. So we train on the training set, we get this learned hypothesis H hat, and we try then out this hypothesis on the validation set. And if the validation error is large, we know that this hypothesis is no good in general. This hypothesis is only good for this training error, so it minimizes the training error. Yeah, I've shown here the corresponding function, Python function that you might use or have already used to split the training, to split the data set into a training and validation set. It's called train test split. Okay, so let's illustrate here this workflow of training and validation using two models. Let's say the first model is the set of all maps or polynomials with degree 1. This is exactly the set of linear functions. So the set of polynomials of degree 1 is the same as the set of linear functions. So this here is linear regression using a single feature. So we assume that data points are characterized by a single feature and a single numeric label. So what we do when we hit the .fit function on the training set, we find the linear curve that has smallest average squared error loss. So we hit the .fit function, we get this learned hypothesis, and then we try it out on another data point that has not been used by the .fit function. And this we call the validation set and the corresponding error. So in this case, it's only a single error. Typically, you have several data points in the validation set, so you have the average loss of all the errors in the validation set. But here's just one, just for ease of exposition. Okay, and with the very same data set, so we use the exactly same data set. Yeah, it might not be reflected by these slides, but it's the same data set. Let's say it's the same data set, but now we use a different model. So we use the same data. The first component stays the same, but we change the second component. We change the model. Instead of degrees of polynomial 1, we use now polynomials of degree 2. So these are polynomials of degree 2. Well, actually, it's not true because, so just a bonus question. Can this curve that I show here, is this a polynomial? Can this be a polynomial of degree 2? No, why not? Yeah, it has two extrema. No? The gradient or the derivative vanishes at 2 points. So this means degree 2 is not enough. It might be degree 3. Very good. Excellent. Okay, so let's say it's model 2 is the set of polynomials of maximum degree 3. Okay, and here, as you might remember from math, when you have at your disposal all polynomials of degree 3, and I give you 3 data points that are not on top of each other, then you will always find a polynomial that passes through these 3 data points perfectly. So you will find a degree 3 polynomial with training error 0. But the validation error might be much larger because you invested so much into perfectly fitting the 3 training data points that you completely ignored the behavior outside this training set. Particularly, you might get a hypothesis that is completely useless outside this training set. And we see this here already with this single validation point or data point, because the validation error is much larger. Okay, so as you have heard in the last lecture, and maybe also tried out in the notebook, you train the models, you compute the validation error for each model, and then you compare the models based on the validation error. And you pick the one, you select the model using the model with the smallest validation error. In this case, it's the one which uses degree 1 polynomials or linear maps. That's the basic workflow in machine learning. That's what you might spend the most of your work time as a machine learning engineer with. Computing training errors or training models, computing validation errors, and then diagnosing the model by comparing the training and validation error. So what we see here for model 2, the training error is quite small. Actually, it should be 0. There's typically always some numerical inaccuracies, so you will not be able to perfectly make the training error 0. Although it theoretically, you find a polynomial of degree 3 that perfectly fits 3 data points almost always. But you might get some small errors still. And but the training error will be much, much smaller than the validation error. And this is an indicator that you overfit. So you just use a too large model or too little data. So it's this dual approach. It's the important thing is, this is already the next slide here. The important thing is always to balance the size of the data. There are different measures for the size of the data. One measure is the number of training data points that you have, M in my notation, and the size of the model. And there are different notions to measure the size of a model, because remember, a model is a set of maps. And already when you look at the simplest model, the most simple model that might come to your mind, which is the set of linear maps from a single feature to a numeric label. So the set of all linear maps, they should be linear functions, is infinite and very much infinite, uncountably infinite large. So how do you measure the size of such a model, which is an infinite set of functions? And there are different ways to measure it. In my textbook, I used a simplified form of a quantity that has been introduced a while ago in machine learning, which is called the VC dimension. It's called after, I think, after 2 Russian mathematicians, Vapnik, Chervenokes. Sorry, my pronunciation. So it's called VC dimension, but I use a simplified form, which is called effective dimension. So it's just a number that indicates how large is a model. And just to get a feeling for this measure, for example, when you look at a linear model, which is the set of all linear maps of n features, it turns out that the effective dimension of this linear model is the number of features. So the effective dimension, which is denoted D, equals the number of features when you use a linear model. And this already shows the more features you use, the larger will be your model, and the higher is the risk that you overfit. So here's already an indicator that you might not want to use unnecessarily large number of features. Another example is polynomials. So a polynomial of degree R, here the effective dimension is essentially given by this polynomial degree. It's R plus 1. So let me illustrate this. When you have a data set consisting of 2 data points, then you can always perfectly fit them using degree 1 polynomial. So the size and one intuitive definition for this effective dimension is the number of data points such that any set with this number of data points can be perfectly fit by some hypothesis in this hypothesis space. So when you look at the polynomial of degree 1, you can perfectly fit almost any data set of size 2, unless these two data points are on top of each other in the horizontal axis. But put aside these pathological cases. With degree 1 polynomials, you can fit any 2 data points. So when you have 2 training data points, you typically will not learn a good linear model, because you will always find, just by pure luck, one linear model that perfectly fits the training data. So when you use 1 degree higher polynomials, so degree 2 polynomials, you can perfectly fit any 3 data points without any problem. So this might indicate that only using 3 training data points might not be enough to learn a distinct degree 3 or degree 2 polynomial. You will always find a degree 2 polynomial just by luck or by coincidence that perfectly fits your training data. You cannot really get more information out of this training set of size 3. So in general, as a rule of thumb, of course, how a machine learning method behaves, if the validation error is large or small, depends on the particular data set. And there are pathological examples, for example, where the validation error is always smaller than the training error. So there are pathological cases. I think one of the exercises will contain such a pathological case where the validation error is smaller than the training error, always. But in general, if you have a sufficient number of data points and you can approximate them as realizations of random variables, then what characterizes the behavior of a machine learning method is the ratio of effective dimension and number of data points in your data set. So there are these 2 factors. One factor comes from the model, the effective dimension of the model or the size of the model, and the other factor comes from the data, the number of training data points that you have. And you want to have typically this ratio of effective dimension to number of data points in your training set to be small. There is typically a critical value, let's call it 1. It's just a matter of normalization of units. But let's say for simplicity that this critical value is 1. So as soon as this ratio D over M is above 1, you typically will overfit. So you want to get this ratio below 1. So how can you do this? Well, there are 2 options, 2 complementary approaches. The first approach might look more intuitive. Use more training data. So increase the number of data points by using more training data. The second approach is somewhat equivalent to the first, but it's just the tuning knob is not the data, but the model. Decrease the effective dimension of the model, make the model smaller. So use a smaller hypothesis space. So let's first look at data augmentation. Data augmentation is a synthetic way to increase your training data. Remember, getting training data might be costly, might be painful, because you need to label data points. You need to have typically some expert who looks at the data point and decides, yeah, label 1, label 0, or yeah, this image shows a cat or this image shows a dog. So collecting raw or real label data might be costly. So people started to look at methods to artificially generate more data. And this artificially generating more label data is called augmentation. And the idea is quite simple, but powerful. So the idea is that typically a data point is always the result of some noisy measurement process, like a temperature measurement. One example of machine learning problem I talked about previously was the maximum daytime temperature prediction. So each data point here, each blue data point might be a previous day for which we know the minimum daytime temperature from the Finnish Meteorological Institute. And then we could say, well, there's always some error in these temperature measurements. When you look at the data sheet or the specification of a temperature sensor, you will typically find some error tolerance bounds, like this is only accurate up to ±1 degree. So there's always an inherent error in the measurements that we get. So even when you download the data directly from FMI, You might say this minimum daytime temperature, the feature of the data point, might not be perfect. It could have equally well have been +1 degree or -1 degree. So you could say in my training set, there could be equally well be a data point which has the same label value, but 1 degree or a slightly different feature value. So there's some wiggling in the feature values of the data points. And you can use this to augment your data. So you say, I don't use only the original data points, but I also use these slightly perturbed data points. We call this the augmented data points. And here in this example, we have just by adding a bit perturbations to the feature values of the data points, we have increased the data set by a factor of 3. So we started with data set size m = 3 because we have 3 blue dots, the original data points. And we then obtain the new size of the augmented data set is 9. So just by adding a few perturbed data points, we have tripled the size of the data set. Yes. And these perturbations, you can generalize this notion, or you can use perturbations in a more general sense. For example, these perturbations could reflect symmetries in a certain application. By symmetries, I mean transformations of data points that leave the label, the quantity of interest, the same. For example, if you have a data point is an image and the quantity of interest is the fact if it shows a cat or not, then rotating the image changes the features. If you use as features the pixel values, the red, green, blue pixel values, these become different when you rotate the image, but the meaning, the label stays the same. So you know more labeled data points. You have more labeled data points. Similar, when you flip the image horizontally or vertically, you get different images. The red, green, blue values of the pixels of the flipped image, they are different. So it's a different data point. However, you know that the label is the same. Or also if you shift the image, the label stays the same. A shifted cat image is still a cat image. Okay, so that was the approach by the data component. So what is the other tuning knob? We can either increase the size of the data set, or we can make the model smaller. We can try to reduce the effective dimension. Do you have ideas? When you start, let's say we start with a hypothesis space being the set of all polynomials of degree 3. How could we make this hypothesis space smaller? Or this model? Yeah, use smaller degree. Yes, that's one way. So we could say this or we could fix some of the weights, some of the parameters. Yes, that's also an option. So we just need to reduce the number of tunable parameters. How could we make the model, a linear model, smaller? A linear model that uses, let's say, 100 features of a data point. Use less features. Yes, when you do feature selection, when you use less features and use a linear model, what you actually do is you reduce the model size, you reduce the effective dimension of the model. Okay, so here's one example. The degree of a polynomial is a parameter. Basically, this degree is the effective dimension of the hypothesis space here. And if you use larger degrees, you have larger effective dimension. So if you have too large model because the validation error is too high, you might say the model is too large, so reduce the model, make it smaller, use smaller degrees. We'll use polynomials with smaller degrees. Another example, quite elegant and somewhat, it's not so obvious at the first look that what it is doing is model pruning, is early stopping. So when you use a gradient method or gradient descent to tune parameters of some model, like an artificial neural network, then basically when you constrain the number of iterations of this gradient descent algorithm, what you actually do is you constrain the effective search space, the effective space of hypotheses that can be explored within 10 iterations. And if you want to explore a larger subset of all possible maps that are represented by a neural network, then you must use more iterations. So 100 iterations would mean a larger search space. So early stopping is actually a way, a means, or an implementation of model pruning. And therefore, a regularization technique. Okay. And now comes maybe the main slide of this lecture today. Regularization is a form of soft model pruning. So we reduce the effective set of hypotheses from which I can choose by solving this empirical risk minimization problem. And we are not doing it by the hard way, by reducing the hypothesis space. So we always have here we minimize this over all the hypotheses in a hypothesis space. So the hard way would be to make this hypothesis space smaller, to prune it. Alternatively, we can still stick with the large hypothesis space, but make it more unlikely to learn a hypothesis without a small subset. And to make this unlikely, we add a penalty term or a regularization term. And you could interpret this regularization term as a form of an estimator for how much larger the loss of a particular hypothesis H would be if it would be applied outside the training set. So this here, what we typically minimize is the training set. This is the performance on the training set. And in regularization, we add a term which uses some regularizer, which could be, for example, the square of the weights. This could be such a regularization function. But again, there is a design choice. There are different options for this regularization function. And this here is an estimate of the of the loss increase when we apply the hypothesis outside the training set. And there are a few widely used choices. They typically depend on some statistical model for the data. So depending on what statistical properties the data points have, you might want to use different regularization functions. And two widely used choices are the sum of squared weights. This is then called ridge regression, the overall problem. So the overall problem is then minimize with respect to the parameter vector of a hypothesis. Yeah, here we talk about parameterized hypothesis. Each hypothesis is characterized by a particular weight vector. Okay, and another popular choice is the sum of absolute values of the weights, which is then called the Lasso. They have different statistical and computational properties, again, because this sum of squared weights, it's a nice function, it's convex and it's differentiable, so we can minimize it easily. But it might be statistically not so accurate, so it might lead to larger prediction errors outside the training set compared to the Lasso, which favors, one striking property or phenomenon of this Lasso regularizer is that it favors weight vectors that have only few non-zeros. So this here results in sparse, we call this sparse or parsimonious models. When you solve this regularized empirical risk minimization for this Lasso regularizer, you will typically get only few non-zero weight vectors. And this can be interpreted as pointing out there are only few features that are relevant, and the rest, the irrelevant features, are zeroed out. But the detailed properties of Lasso is way beyond the scope of this course. There are excellent advanced lectures about the Lasso methods. Okay, yeah. And it turns out, for those of you which have already had some course on optimization, what we actually do in adding this regularization term, we could interpret this as this is called a Lagrangian Lagrangian term, and this here is then called a Lagrangian multiplier. And the such Lagrangian multipliers are used to encode additional constraints. So the constraint that the hypothesis should belong to a pruned hypothesis space can be often represented equivalently by adding a regularization term. So this is just a dual form of model pruning. And you can then actually work out how this choice of lambda, so lambda is then a hyperparameter of the method. You might try out different values and look at the final validation error to find a good value. But if you're familiar with optimization theory, you could work out a precise relation between this lambda and this pruned hypothesis space. So you know, if you want to prune your hypothesis space, let's say to a given size, you could come up with formulas for this lambda. So how to choose the lambda, this regularization parameter. But again, this is way beyond the scope of this course. We just use regularization as one further tool in our toolbox. So you can look at it as a specific choice for the loss function. So you can say we construct a loss function that not only includes this squared error loss for each data point, but also includes some term that measures the complexity of the hypothesis. So you can just look at these regularization techniques as a specific design choice for loss functions. Okay, and now for the final part of this lecture, I want to point out a nice and maybe also very useful connection between these two approaches. So remember, our goal was to balance the size of data and the size of the model. So we can either increase the size of the data by data augmentation or reduce the size of the model by regularization techniques or by soft model pruning. A regularization technique essentially reduces the set of possible hypotheses we learn from. But it turns out these are equivalent. And let me explain in which sense. So the basic idea of data augmentation was take any labeled data point and add perturbed versions to it. So instead of one data point, we add many more data points that are obtained by just adding a bit of perturbation to the feature. And one very elegant way and principled way to add perturbations is by a probabilistic model. So you say, I look at all perturbed data points that can be obtained by randomly drawing, for example, a noise term from a Gaussian distribution. So we add to this data point an infinite number of realizations of a small noise variable. And so we get augmentation factor infinite, because we replace this single blue data point by all possible realizations of a Gaussian distribution. And you can infinitely often draw from a Gaussian distribution. There's no limit to it. If you have a random number generator, you just draw one draw after the other, get a new realization of a noise term, add it to the blue data point, and you get a perturbed data point. Okay, so when you write down then for this augmented data set, empirical risk minimization, you can collect terms. So you can write down the average loss on this augmented data set. So this would then be a sum over 9 components. So let's just forget about if it's blue or orange. Let's just say we have 9 data points for which we know the features and the label. So we write down the training error using a training set of size 9. But then we could say, but we know a bit more about the data points. So we separate terms. You write down this whole sum into one sum that only contains the original data points, the blue ones, and the second component that only contains the perturbed data points. And then it turns out this sum that you get becomes an expectation in the limit of infinitely many of an infinite augmentation factor. So when you use an infinite number of these perturbations, you get here a sum that converges to an expectation. This is again an application of this law of large numbers. So if you should learn something about probability theory, maybe one of the most powerful and practically useful techniques or concepts is that of approximating approximations by sums, by a sum over many IID realizations of a random variable. And this is called the law of large numbers. And using this law of large numbers, you can show that the sum that you get over these perturbed data points becomes an expectation. And this expectation depends only on the hypothesis. And this expectation is actually this regularization term. So this regularization term here is an expectation and is, in a sense, an approximation in the other direction. You can also consider an expectation to be an approximation of a sum, of a large sum. So you can view this regularization term as being an expectation that approximates a large sum over perturbed or augmented data points. So it turns out that this data augmentation and regularization, they are equivalent. They are connected by the law of large numbers. Regularization uses the expectation. Plain data augmentation uses a sum. When you use more and more components in this sum, it comes closer and closer to the expectation, which is the regularization, the regularized form of this data augmentation. And yeah, what is nice about this? I mean, for me, it's nice conceptually. I love these mathematical symmetries and results, but also practically, because a challenge in using these regularization techniques is always, how do you choose the regularization parameter? How do you choose lambda? And of course, the standard option always, when anybody asks you, how do you choose this parameter? You can always say, well, I try out many different values and pick the one which gives the best performance in the end. The best performance could mean best performance on a test set or on a validation set. So that's the standard answer. But here you could give a bit more advanced, a bit more how should I say, elaborate answer by, you can choose this lambda, or you can interpret this lambda as the noise strength here, as the variance of the noise. So this variance that you use for adding perturbations is directly linked to this lambda. I have worked this out in my course book. I'm not sure if there's a factor between it, but I think it's essentially somewhat proportional. It should be proportional. So this lambda is proportional to this variance of this data augmentation. So you get an interpretation, a neat interpretation of this lambda that you use, for example, in ridge regression, is equivalent or proportional to the noise variance for a data augmentation approach. So the larger the lambda, the stronger the noise that you use for data augmentation. And here you see already, when you use a very large lambda, you basically augment your original data points by many widely spread augmented data points, which forces the learned hypothesis to be horizontal, basically, because this augmented data set is aligned on a horizontal line. Okay, that's it basically for the theory block. So to sum up, the practice of machine learning often amounts to balancing two sizes: the size of the data, which is here denoted M, and the size of the model, which is denoted D, or effective dimension. I would say 90% of the everyday life of a machine learning engineer is about balancing these two quantities to get D over M small. And one way to reduce, so there are two approaches to do this. Either try to make this effective dimension smaller by making the model smaller. And you can make the model smaller by just using a smaller model, using lower degree polynomials, using smaller artificial neural networks, using less features. So this is called model pruning. It's a very discrete and rough way. And a bit more elegant or soft way is by regularization. And regularization is a soft model pruning that can be obtained by adding a regularization term to the loss function. So it's pragmatically speaking, a regularization amounts to a specific construction of a loss function. And the effect of this different loss functions is to reduce the effective size of the model that we optimize over in empirical risk minimization. So this affects a soft model pruning. Okay, but it turns out actually that this soft model pruning is equivalent to a form of data augmentation, using an infinite number of perturbed copies of the original data points. And these perturbed copies are obtained by realizations of a small noise random variable. And this expectation over this noise random variable is exactly this additional term in the loss function, this regularization term. Okay, that's all about regularization. I suggest we now have a bit of a longer break, let's say 10 minutes till quarter past 3, when then you will hear about machine learning applications, practical machine learning applications, by Dr. Nuti Sten from the city of Helsinki. So Nuti is a data scientist at the city of Helsinki, and they have really a lot of exciting machine learning applications to work on. Okay, see you in 10 minutes. Hello, Nuti.
Hello. Can you hear me?
Yes. Would you like to share slides?
Yes, I will.
Yeah, could you try out if you can share?
Yes. It says that host has disabled participant screen sharing.
Yeah, I have made you now co-host.
Okay, let's try again. Oh yeah, now it should work. And now you should see my slides. Yes.
Yes.
And now you should also see my face.
Yes. Hello.
Okay, so yeah. So I'm giving it a talk, and then we have a Q&A session after that. Will you host the Q&A session? If I share the slides, I'm not sure if I see the comments.
Yes. So now the slide is blank. I don't know, is this intentional?
Yes, it's a like first slide. It's intentionally blank.
Good.
So how's the course been going? You had lectures since the beginning of the year, or?
Yes, we are now in the middle of the course. The exercises are running.
Yeah,
And
I see.
Machine learning project stage 1 is due soon, where the students have to formulate an application as a machine learning problem.
Yeah, I see. This is a big course. Is there? I see 200 participants.
Yes, so in this coding assignments, we see people active around 770.
Oh, wow.
Yeah. By the way, are you
massive.
fine with recording your talk?
Yeah, of course.
Yeah. So that's why I guess we don't have so many now in this meeting. We always put the recordings online and.
Yeah. That's well. By this time, I hope most of the students have already woken up, but
yeah.
But they might have something else to do. Yeah, but 200 people attending is still quite a lot.
Yeah.
I don't think they had this massive courses when I was still studying.
Yeah. And did you enjoy the snow over the weekend?
I couldn't. I had my third vaccination last week, and I was pretty down.
Yeah.
Throughout the whole weekend, which was same because they were really like. I like to do backcountry skiing and also off-piste snowboarding, so could have done either of those, which is like pretty rare here in Helsinki area, like to go actually go about in the nature. But
where's the next opportunity for snowboarding next to Helsinki?
They have these small hills, like one in middle of Espoo, Granibakka, and then in Kirkkonummi there's Peuramaa, and then Vihti is it close to Lohja, so like 30 minutes, 45 minutes drive. And then of course if you go a bit further you find a bit bigger hills. I think Messilä is the biggest one.
Yeah.
But yeah, I usually like to go to the Alps, but for a couple of years, for obvious reasons, haven't been able to do that.
Yeah. Which part? Tyrol?
I like the Italian Alps because of the food.
Yeah, that's true. Yeah.
But Austria is also nice. They have a bit steeper slopes.
Yeah.
Okay. I see there's a question in the chat for you, Alex.
Yeah, so there was just one question now about the if the number of features is large, is it really so that the effective dimension of a degree 2 model is smaller than that of a linear one? So what I was talking about for these polynomial models did only apply to scalar features. So only if you have one real number as features, then the degree of the polynomial is essentially the effective dimension. And yes, if you have a single scalar feature and you use degree 2 polynomials, then the dimension is essentially 2. But if you use only linear models, but 100 features, then the effective dimension is 100, larger than for degree 2 polynomial, but which only uses one single feature. Okay, 1 minute to go. And Nuti, do you know people who are responsible for the scheduling of snow plows in Helsinki? I assume this is a hell of a job.
Yeah, I guess so. Haven't run into them yet, but I assume that they would have some interesting computational issues.
Yeah. Also the prioritization, which streets first.
Yes. And I would like to see if it how neutral are they? Do they plan, like if you're the guy sitting in the planning office, is your home street always clean?
Okay, that's a good point. We could check this with data science. Okay, so the break is over. Welcome again to Nuti Sten. He is data scientist at the city of Helsinki, and I'm looking forward to what he has to tell about machine learning at the city of Helsinki.
Yeah, thank you, Alex. I would like to correct one thing. I do not have a doctoral degree, at least so far, so that is still something to achieve. But yeah, I want to start the talk with a sort of a metaphor, because I like those. So comparing machine learning to something that we are all familiar with, and sort of leading you into the topic of the day. So I think, in my opinion, machine learning is quite like nuclear power. It's difficult to set up. It's sort of one-way ticket. Once you build up the whole system and become dependent on it, it's really difficult to take it down safely and replace it with something else. And there are huge risks involved if something goes wrong. With machine learning, you're either dealing with sensitive data, or then your algorithm may have effects in the real world, and you want to be sort of certain how it works. Just as with anything else that has impacts people in the real world. And okay, wrong window. Yeah, no. Yes, now I can again change my slides. Yes, so the part that you're sort of learning in the university is typically very restricted and controlled. So in this course and many other courses, you probably have very like really provided environment and instructions on how to build up and set up your machine learning systems and how to run them. And you actually don't even have to care about like whether it affects you something or not, because you're only fitting models to real data, but you're not applying the model in practice. So there's no real interaction with the machine learning models that you use. And so you don't even have to care about building up the laboratory or then building up a whole power plant of machine learning. And that's sort of the topic of today, is how do we build everything around the algorithms themselves so that we can actually utilize machine learning in practice. So as said, I work at the city of Helsinki. You might ask, why does the city of Helsinki do machine learning? So a couple of words there. Of course, you know, capital of Finland and so on. We like quarter of the population lives in Helsinki, etc. So we have a lot of people. We deal with a lot of national and even European and global level issues. And few of these issues that we especially want to tackle with in all our actions are, first of all, the dependency ratio, and second of all, environmental crisis, in no particular order. But these two things are the sort of two driving forces for anything that we do besides the basic functions of the city. So we want to tackle these issues. And with machine learning, we can tackle them in two ways. We can do proactive services, which means that we can find potential customers of our services and predict their needs, possibly even before they themselves realize that they have a need for some service. This could be, for example, in healthcare or in social services or in employment services. We can bring the service to the people without them having to sort of dig for it as it is at the moment. The other focus point is on changing the mindset from descriptive analytics to predictive analytics. So traditionally, large organizations and especially the government side, they have focused on statistics, collecting statistical, very clean data, manually processing it, providing these reports that state that what does the data contain, describing the data. But in machine learning, we are actually not interested in the data. We are interested in the data points that we do not have. So we are making predictions. And that's a huge shift. So a typical machine learning system in practice would look something like this. So we have a service which consists of a customer. This might be a professional who's using a very smart tool. It might be an end customer, like someone who's visiting a healthcare center or hospital or something else. And then we have the sort of front end, which is the fancy application, and then a backend side, which runs all the heavy tasks. Then we collect data from the customers, or it can be from other data sources. Usually we combine multiple data sources because that's the power of machine learning too. And then we need to, first of all, set up the machine learning algorithm so that it can predict our data. And for this, we have this sort of lab environment, a system for updating our machine learning model and also making changes to it. And then another system where we can then run these trained machine learning algorithms. And these two are what I'm focusing on my speech today. A quick note, everything here is sort of Python-centric, but the principles that I'm presenting are applicable to any language or Julia, whatever you're using. It's about writing data code in a way that it's applicable and easy to use. So the language really doesn't matter. So you can Google up and probably the specific tools might have different names and so on, but they all follow the same fundamental principles. I've divided the speech in sort of two parts. First is about creating applicable machine learning. And this is the sort of best practices for building a machine learning model that you can actually then deploy to some as part of some system. And then the second part is about then running this trained model in action and interacting with it. Starting from the very fundamentals, I want to include this because I think it's like the easiest way to write good data code is to follow the tidy principles, which is a set of principles introduced by a long-term R developer, Hadley Wickham, who has written these tidy data and tidy tools manifestos. You can Google them up, and I highly recommend reading those. So they sort of describe you first how to formulate your data in a way that it's easy and efficient to analyze. And so it means that you should always formulate your data into a very clean two-dimensional table, where each row is a data point, each column is a feature or label, and each cell contains a single value. This might sound simple, but in practice, it's like a common mistake that you take in some data in some very weird format, and then it's really hard because we have to pass it to different functions, and if they don't handle the data in same format, it's like easy to get very messy output. And all the standard tools that you've already been using, they assume these principles already. There's one exception to this, and it's basically kernel-based methods. So if you're processing, for example, image data, it might be that your data point might be a nested structure. like a vector inside a cell, but that's an exception. The tidy tools then tell you how to write code for handling this tidy data, and they consist of 4 principles. The first is reuse existing data structures, which basically means to use tidy data and use the common formats for your data, so the data types should be like sensible for the data. Then the pipe operator, which you are also familiar with probably. So you know that in Python you can like link and chain these functions together with this dot operator. So you call a function, then put a dot and another function if they are like class functions. And this is because of the way they are built, and you have to build them in a specific way so that you can pipe them. And this means that each function should only do a transformation, which means that it takes in a value, it modifies this value, and then returns this modified copy of the value. Or then you do a side effect, which means that you alter a state of an object, and then you return reference to this object. And you never do both. You only do either one of these, because then you can intuitively write code using these functions, and you can always trust what the function is doing. The third point is quite R specific. It's about embracing functional programming, but Python is not functional programming language, but we can sort of translate this into Python by stating that you should always utilize vectorized operations when possible. This means the apply and map functionalities. They not only perform the operations computationally more efficiently, but they are also, again, easier to read and write. Which brings us to the fourth point of designing for humans. So you should always write your code so that it's as easy to read and write as possible. And this is because like code efficiency is really it's secondary. If you can like it doesn't matter if your code runs for 2 days or 3 weeks if you spend half a year planning the code. So you should always try to first minimize the time that you spend creating the code than the time that the code runs. I have a couple of examples from here. First, this is what you should not do, but quite of many of you probably have done something similar to this. So here we break almost all of the rules. I tried to create an example where I break every single rule at least once. So here we have a model wrapper that sort of wraps the linear regression model. Actually, you wouldn't need this class to wrap this simple model, but I did this for an example. So we have a model that takes in data, and it takes it in a non-tidy format, a custom format. And this makes it challenging because we have to then modify the data inside the model. And we then go even further and make a copy of the data, which is again bad because then it breaks consistency and causes all sort of reproducibility issues. Then the functions they are not named clearly. Functions should always be named with verbs and be very descriptive of what the function is doing. And then we break the transformation and side effect rule. And because of this, we cannot pipe the functions. So we need to write many lines of code, and all of this is very hard to read on. If you try to read the code and make sense of what this is doing, it's very difficult. But this is quite common. You see this quite often, unfortunately. Here we try to then fix this and rewrite the same wrapper in a tidy way. And here we don't include the data inside the model. We only accept tidy data, and we name the functions with verbs and don't break the transformation side effect rule. And this way we can actually create this in a quite familiar way. This function, we can use them, using the pipe operator. So we can make these one-liners where we first create a model and then we feed it to data. So this is quite handy. And you can actually take this to quite long extents. So you can actually create quite complicated operations just as one-liners. Of course, there's a limit to what you should actually push this into. But you already see that you can just take a glimpse of the code and you know what's going on there. Even if there are not many comments here, and you can still read the code very intuitively. You can find the code examples in my GitHub page and try out them yourselves. You notice that I used Jupyter notebooks in my examples, and this is because basically notebooks are the one way of doing data code, and this is because you want to see what's happening as you code. So you write some piece of code, you run the code or the part of the code that you just wrote, and you see the result. And that's the beauty of Jupyter notebooks. You have the code, results, and documentation as one. It also allows you to ease up on testing. Testing machine learning is quite difficult because it's very difficult to formulate these exact tests when you don't necessarily know what's the right answer. Of course, there are very advanced high-level testing frameworks that you should utilize, but still you need some sort of traditional testing usually to build secure software and functioning software. So if you have a well-defined notebook, if you can run this notebook, you already have a piece of test. And also you can separate your work into multiple notebooks, and each notebook then consists a workflow component. And then you can parameterize and automate the run of these notebooks. There's a tool called Papermill that allows you to run Jupyter notebooks as functions from inside Python. So it's quite handy. You might ask, how about copy pasting and can you actually create good code with Jupyter notebooks? Yes, you can. There are tools for this. For example, this nbdev tool, it allows you to move code from notebooks to a Python script automatically. So you don't have to do it the old way of first writing a notebook and doing a demo on the notebook and then copy pasting the code inside a Python module, and then suddenly everything breaks down. And it's really hard to say which part of the code is right and wrong when you have so many copies of the code. So this does it all automatically for you. Yet another mistake that people make quite often, you're eager to see the good results of your algorithm, and then you take in a whole lot of data and you begin your development, and it just takes ages and ages to run your code. And then you repeat this multiple times, and then you end up using like 100 times more resources for the final product, and a lot of sweat and tears. So make sure your code works as code before you actually move on to the evaluation phase. So do this by first beginning your development with a tiny sample of your data. Only 10 or 100, maximum 1,000 data points. And only then, when you're sure that, okay, now this really works, then you can include more. Also, you should try to write your code in a reusable way. This means that, of course, you can begin with scripting, and with notebooks, you have this small scripts there that you run. But then when you sort of get an idea what you're about to do, and then you see that, okay, I need to do this over and over again, start to write functions and classes, because then you can parameterize them quite easily. If you end up having scripts, you should also parameterize those. You should parameterize your notebooks, everything. And as said, you should also split your code into independent components. So if you have a part of your code that deals with your data, and then you have a part of your code that deals with your model creation, you should not sort of entangle these. So it's best if you can even separate them into separate files, separate notebooks. And for machine learning, of course, the logical division is to first have a notebook for processing your data. You usually have to do quite a lot of data cleansing, even some basic data analysis, before you move on to defining your model. And that's the second part. And then when you have defined your model algorithm, then you can actually train and evaluate it with the whole data set that you have. And so here you have a like three-piece workflow. And if you then automate the run of these notebooks, you have now, you can actually then like with a single command, redo everything in your workflow. Again, if you have a notebook or multiple notebooks where you have to manually click or run several cells, that's not very reproducible. But only when you can actually like execute single command and everything will be redone, you can then have reproducibility and scalability. You can solve different issues that are similar to your previous issue with the same tools that you just created. There's two types of workflows. First is a static workflow. So we can define a master script that runs these other notebooks. Or then you can have a dynamic workflow, which also takes into account what has changed since the previous run. And for this, there's this tool, for example, this SnakeMake tool. So it allows you to track where is my change. So if you have, for example, you have already prepared your data, and then you change something in your model. You don't want to rerun the model, the data preparation part. You only want to run the model creation and model evaluation parts because they are affected by the change. This should be quite obvious. Use seeds whenever possible. It's not always possible to use seeds, but even then you should use seeds where you can. So, for example, if you have some very high-level multi-runtime machine learning model, but you're still doing the data preparation the good old way, you can seed the data preparation part and have partial reproducibility from the seed. But use seeds every time. Of other thing that should be also like taken for granted, reproducibility, you need to have version control. You need to be able to return to previous stage of your code and maybe change some things, try out different things, and it makes your life much easier. Also allows this shared work on software, and it doesn't. It's not enough that you take into account your code, but you should also version your data environment, the parameters that you use, the seed numbers, everything that you have that can change the output of the model. And Git is not quite enough for this. So if you have a lot of data, it's not good practice to include it in Git. Of course, there is the Git large file storage, but that has its limitations too. So there are these other tools, for example, data version control and flat data, that are designed for tracking changes in your data without messing up the whole GitHub repository. So that you can actually then reproduce the code, you need to also track the environment and you need to control it. Of course, this means dependency requirements. For this, by the way, I recommend the pip tools. It's a sort of upgraded version of pip. It's a bit more strict on the exactness of the code versions that you're using. As you know, open source tools, they are dependent on other open source tools, and then if changes are made to those tools, they will also affect your work if you don't keep track of which versions of the code pieces you used. You might be familiar with using virtual environments. That's a good start. Ensures that your project is not mixed up with other projects on your same device. But then if you want to go like a step further, I recommend getting to know containers, because container, it sort of insulates your project from the device that you're running in or the environment that you're running in. and creates this mini virtual machine. And so then it really doesn't matter where are you developing, you always have the same environment. So that's all of the brief steps into writing good applicable machine learning code. And then we're moving on to the next part, which is then applying machine learning, setting it up in an environment where you can actually interact with it. And this is a practice that's quite commonly referred to as machine learning ops or machine learning DevOps or data ops. They all mean the same thing. It basically all means that you try to build up your system so that you can sustain the performance of the machine learning algorithm and create value with it. And the first part of the speech sort of tried to explain why you can't treat machine learning as traditional statistical analysis. So you need to apply it. You need to create it in a way that you can actually interact with it. And now this part of the speech is quite about why you can't treat it as software. And it all comes down to change. So with traditional software, you have quite predictable change. And you can set up a system and it runs as long as you change it. And then every change you make, it's controlled and you decide when do you do it. But when you incorporate data and start building on top of data, it changes quite rapidly. Because now, if the data changes, your model might not perform as well as it did before. And so it might be that you really don't, even if it worked yesterday or 2 weeks ago, your model, it just suddenly stops working. And so you're now dependent on the updates from the data, and you need to constantly recreate the model that you are using, retrain it and upload it again. And to do this, of course, we need to collect new data and then retrain the model and have some sort of criterion on what's good enough. So we need to make sure that whatever we put into production is sort of working good enough. And for this, you need some sort of acceptance criteria. It may be your loss function value, it might be something else too. For example, the sort of uncertainty values of the predictions. And for this, it's also very important that you really do split the validation data. Quite often people only split the training and testing data, but then you really need this separate validation data that the model has never seen. And it's best if that data is something that is like fresh, that's being collected just like recently. It's the more freshest data that you have, because that sort of tells you how well your model will react to these changes that it has not seen in the data. And it's quite tempting to, for example, rerun your model training script until you get sort of almost good enough results, because there are often random processes involved, and this is something you should not go for. So you run the script, if it passes, it passes. If it doesn't, you really like dig deep and see where the problem is. Then deploying the model, you of course need an API. There are Python tools for this. There are tools for other languages for this. So this is just a standard way of interacting with your model, so that it's like other systems can do it easily. And you need an environment where you can run this, and this has of course some new specifications. In a lab environment, you can control how much load is put into the model, but in real world, it might be that someday you have like 1,000 customers and then you have 10,000 customers the next day, and you need to be able to scale your resources based on this. And when you finally get it up and running, you need to constantly monitor your model performance. And something that will happen is that your model performance will decay. And once it passes a certain level, you need to retrain your model and put it on production again. But again, this is not enough. You need to also keep track of your business metrics, because it might be that your model is poorly formulated, or it's just irrelevant, or your data is sort of flooded with something that should not be in your data, and then your model might have like zero effect in your business, what you're doing. And with business, I mean like anything that you're doing with the machine learning model. It doesn't have to be like acquiring more money now. It can be just like customer happiness or whatever you're trying to achieve. So collect business metrics and monitor them. And if there's any change in data, model performance, business metrics, you need to re-evaluate your model and possibly make changes to it, retrain it, and so on. There's quite a lot of stuff that we've covered so far, and it's a good reminder that this is not like a one-person job. There should always be a team or multiple teams and well-defined roles in an organization so that they can actually apply machine learning. So otherwise, it's too fragile, and it will break basically immediately. It just cannot be done by a single person alone. And this is something good to remind if you want to ask good questions in a data science interview. You can ask them about how they organize their roles around data and machine learning. I'm not the only person to sort of collect this sort of knowledge, and I do have collected this information from many sources. So there's a lot of these best practices and the patterns from the industry. So it's like a lot of good knowledge, but also bear in mind that these have like a limited perspective. It's usually from just one organization, and then they might have some sort of hidden agenda. In Finnish, we have this saying of having your own cow stuck in the mud, which means basically that you're sort of trying to sell your own product, or then you're not telling the whole truth because you don't want to, who knows, give advantage to your competitors or something. So just bear in mind that it might be that there's something like this in there, but in general, a lot of good information, even though it's not scientific. Of course, I do have my own cow in the mud. So a couple of tips from our side, a couple of tools, open source tools, data sources that you can utilize in work, school, some of them even in this machine learning project that you might be working for this course. First of all, we have developed this GitHub repository template for easily developing machine learning applications. It's open source. You can check it up for thesis work, research work. For this course, I think you have quite specific requirements for developing your work. So please check compliance before using it for this course. But for any other work, go ahead. We also have a tool for anonymizing data, and I think it sounds simple, but it was surprising to me that there was so little like general tools for anonymizing data when I began work here like a year ago. So this is something we've been working on for a good half a year, and now it's working. So if you need to, for example, process personal data, want to anonymize it, this is a good way to go. Then if you want to get data for your research projects, also for this course, we have the Helsinki region Infoshare service. It's an open data service that collects data or sort of links data sources to data users from Helsinki region. And here are even a couple of project examples that Alex asked me to prepare for you if you want to take the challenge. But of course, there's more. Go and find yourself. Now, this was everything from me. So my name is Nutis, then I'm a data scientist at the city of Helsinki, also Aalto alumni, and happy to hear any great thoughts that you will have in the future about data and machine learning. And now I think we can move on to the question section. So go ahead.
Thanks a lot, Nuti. Very interesting talk. I have here collected a few questions I will forward. So the first one was, how do data scientists usually do version control for their Jupyter notebooks? From what I have observed, Jupyter doesn't work that great with Git.
Yeah, because Git is checking differences in your lines. So it's a line sort of checks which lines change. And Jupyter notebooks, they don't have this line structure. So it's difficult to sort of track the changes, like line on line changes. But recently there have been these tools for this. For one is this NBDev tool that I mentioned. It has a support for notebook version control, and I think the Elira notebook pipeline tool that I also mentioned, I think there might be another tool for this. So I think it's becoming a thing now, because people have realized that they really need version control for their notebooks. But if you have small notebooks or you're just working alone, it really doesn't matter that much.
Yeah. Thanks a lot. So next question was, do you always have access to GPU, or do you prototype on laptop with small data and then move to cloud-based GPU services?
Yeah, I do have access to GPUs, but of course they are expensive, so I usually do my development in a smaller environment, and then only if you need to run something like heavy, then you go into the expensive resources.
Yes, thanks a lot. Then the next question, is there any de facto ready-made MLOps framework? Also, how is it different from traditional DevOps?
Yeah, so the whole DevOps and MLOps things, they are concepts for setting up your machine learning work at an organizational level. So it's not a single tool, or it's not a single sort of set of rules. It's a sort of combination of these, and you need to figure it out per organization. So it cannot be sort of, you cannot buy it off the shelf. But of course, there are tools that help with this. For example, GitHub has these like DevOps tools that you can utilize for that work. But it's yeah. So it's like you need to define it for the organization that starts implementing something. And for MLOps and DevOps, the difference is what I mentioned, is where the change lies in. So in MLOps and any database products, you need to account for the change in data that you're relying upon. In traditional DevOps, all change is basically planned, or at least in the mindset that we have, like the change is so much more rapid in machine learning.
Okay, thanks. Then the next question was, what is the difference between data engineer, data analyst, and data scientist? And how much % is used for data cleaning? How much for hyperparameter tuning in the typical machine learning applications?
In an ideal world, I would say that the data engineer is sort of the guy who sets up the infrastructure for running the data operations, doing development, running the trained models in action. They might also do some of the data preparation, but it depends. Yet again, in an ideal world, a data analyst would then be doing this sort of more traditional descriptive analytics of the data, and also sort of linking it to the business understanding of the organization that they're working for. So it's more like traditional statistics and describing the data. And that's sort of the order of execution also. Like first we have the data engineer, they come and build the working environment. Then you would have the data analyst do basic analysis, and then the data scientist comes and sort of applies these predictive methods. So, but in real life, all of this is sort of mixed quite commonly, I guess. So you have to at least understand the basics of each of these, or you will learn to understand the basics of each of these. But maybe in the future, I don't know if in 10 years it might be that people can actually focus on one thing.
Yeah. Okay. Then the next question, is there any need in your domain for running machine learning inference on edge devices, especially on tiny devices like microcontrollers or IoT sensors?
This is an interesting topic. Yes, we, for example, at the city of Helsinki, we have tried these, for example, these devices that measure air quality around the city, and also counting different types of vehicles based on video footage and this kind of stuff. And I think it's like an upcoming trend, these IoT devices, and it's then you of course want to do as much of the computation in the edge device as possible, because you don't want to be moving information and huge loads of data from the device to cloud or any other environment, because that costs a lot of money and there's latency.
Yep. Okay. And then the last question I have here, do entry-level machine learning positions typically assume the ops skills, or are they a separate role on their own?
Well, this depends on the organization, how major they are and so on. So like for entry-level positions, that there are still, like, unfortunately little in the data world. I think there's this like the big trend has been that you have to have like at least 5 years of development history and something, but I think it's now changing. I myself, I don't have a developer background, so I went straight from school to being a data scientist. So I think it's like people have realized that it's more than just and it's different thing from doing traditional software to do data products. And of course, the better you know things, the better. But I think it's good to have at least like have some sort of basic understanding what the terms mean. And I think yeah, I actually prepared, like, because I anticipated this sort of question, so I prepared a slide for this sort of, in my opinion, set of skills that you would like, or at least if you can showcase some of these skills, then I think you're good to go. Like at least have like 5 or 6 of these skills, then you're good to go for an like entry-level position. And what's also like I think an upcoming trend is that the data scientists are more and more focused. So it's good that you have like a domain of expertise outside the ICT world. So you're like really good at something else too, because especially the data scientist role, it requires you to understand the topic that you're modeling and the needs of the client, because ultimately, you know, you're not like creating a good loss function values, but you're creating value for the issue that you're sort of solving.
Yeah, here one question. Could you pass on a copy of the slides if I have received from you, but I'm not sure
yes,
if you changed.
Yeah, it was a draft version, but I will send this updated version for you so you can share it with the students. Yes.
Thanks a lot. Okay, thanks a lot again, Luti. Very interesting glimpse on how machine learning is used in a big organization. I guess City of Helsinki is one of the, if not the largest employer in Finland.
Yes, that's true.
Yeah, very cool to see this. Thanks a lot again. And yeah, unfortunately, we cannot give an applause. I try to. Thanks a lot. And yeah, we see each other then on, I think on Wednesday, when Professor Sig will talk about deep learning. Yeah, thanks a lot again. And Have a nice rest of day. Bye.
Thank you.